nucleophilic substitution reaction. Reactions. Okay. The idea is this. What is meant by nucleophilic substitution reaction? See, we will be having a molecule, okay, which has some group which is ready to depart from the molecule, and we have an attacking species called nucleophile. Usually in nucleophilic substitution reaction, nucleophiles carry negative charge, but nucleophile can also be neutral. Okay, the essential point is it should be electron rich. It should contain at least one lone pair. Okay, and this molecule, I'll call this molecule as a substrate. This molecule is called substrate. Okay, where the nucleophile going to attack. So the nucleophile attacks the substrate. Okay, so what will happen? This leaving group, or the group, right, which is present in the substrate, it may be an atom or maybe a group, it will come out. This is basically a nucleophilic substitution reaction. Okay, some group is substituted by another group. Right. In nucleophilic substitution reaction, I have told you there are many types. There are many types of nucleophilic substitution reaction, but we are going to discuss only Sn1. We are going to discuss only Sn1 nucleophilic substitution reaction, Sn1, Sn2, Sni, and SNAR. What are these? 1 represent unimolecular, N represent nucleophilic, S means substitution. So unimolecular, unimolecular nucleophilic substitution reaction. Sn2 means bimolecular nucleophilic substitution reaction. Sni means intramolecular nucleophilic substitution reaction. SNAR means aromatic nucleophilic substitution reaction.
Sir.
Yes?
Sir, we've learned only Sn1 and Sn2 in school, sir.
Sn1 and Sn2 only, right? Yeah, but Sni is there, Sni and SNR are also there. Okay, they won't teach this under mechanism, but it will come automatically, right? Yeah. Then, okay, we'll move further. So these are all different types of nucleophilic substitution reactions we have. These are all based on mechanisms. Okay. Now, okay, let's start our discussion with Sn1. Sn1. Sn1 means, I have told you, unimolecular nucleophilic substitution okay, reaction. Unimolecular nucleophilic substitution reaction, that is Sn1. Okay. In Sn1 reaction, the mechanism actually consists of 2 steps. Right? Mechanism of Sn1 reaction consists of 2 steps. First, I'll write an example for Sn1 reaction. Sn1 reaction preferably occurs on tertiary halides. So, first I'll write an example here. Example for Sn1 reaction. I'll take a tertiary halide. Some tertiary halide, CH3, 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 bromine. Tertiary, this is called tertiary butyl bromide. I have given common name here. This is not IUPAC name, it's a common name. Tertiary butyl bromide, or IUPAC name you can say 2-bromo-2-methyl propane. To this, if I add aqueous sodium hydroxide, right, what will happen? nucleophilic substitution will occur and you will get this product. That is, this bromine is a leaving group, it will come out, and here this sodium hydroxide will ionize to give Na plus and OH minus ion. The OH minus ion will attack this carbon. So OH minus is the nucleophile here. OH minus is the nucleophile, and bromine, this bromine atom is the leaving group. It is called leaving group. Okay, in leaving group, and this molecule is called the substrate. Substrate is the molecule where the nucleophile attacks. Okay, in the case of nucleophilic substitution reaction. So what will happen? Bromine is replaced by OH group. So you will get this compound, CH3, 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 OH plus bromine comes out as Br minus, and the solution already has Na plus ion. Okay, this is a nice example for Sn1 reaction. Students, keep this in mind. For Sn1 reaction, we preferably take tertiary halides. Why? Because tertiary halides are very suitable substance or molecule for Sn1 reaction. Okay, now I'll give you the mechanism. Okay, this reaction occurs in two steps. So what is the mechanism of this reaction? Okay, Sn1 reaction, the mechanism of Sn1 reaction, right, occurs in two steps. There are two steps. Students, keep this in mind. Sn1 reaction occurs in two steps. Okay, I am just giving the mechanism of Sn1 reaction. In mechanism, we have two steps. What are the two steps? Step 1. Step 1 is nothing but ionization of the molecule. Okay, ionization of substrate. Okay, let me write here, ionization of substrate molecule. Okay, this is this step 1. And after ionization, okay, ionization, not only ionization occurs, in this ionization you will get a carbocation, and a carbocation is generated. And a carbocation is generated. Okay, in step 1 the substrate molecule undergoes ionization and hence a carbocation is generated. Okay, let me write the step here. So the tertiary halide is the substrate here, tertiary butyl bromide I have taken. This is an example. Okay, you can take any example. I chose this, tertiary butyl bromide. What is the first step? This is called the substrate molecule. Substrate molecule. What it will do? It will undergo ionization, okay, in the solution. Right, ionization takes place. Right, listen. This C-Br bond, where bromine is more electronegative, this bromine takes the bond pair and comes out as Br minus. You know very well, each bond contains 2 electrons. Bromine atom, since it is more electronegative, it will take both the electron and comes out as Br minus. But the carbon losing the electron, now it becomes a carbocation. Okay, let me write the structure like this. CH3, CH3, CH3 plus. Now a carbocation is generated. Okay, so this is the first step. Substrate molecule undergoes ionization. Ions are produced. Neutral molecule producing ions. So it is called ionization. Right? In this ionization, we get a carbocation. Students, keep this in mind. The rate of this reaction. Okay, actually this reaction is a slow reaction. This reaction is a slow reaction, right? You know very well, or if you don't know, you just keep this in mind. In mechanism may contain one step. mechanism may contain 2 or more steps. The step which takes place in a very slow manner, that step is called rate determining step, RDS. What is RDS? Rate determining step. I repeat, the mechanism of a reaction may contain single step, or the mechanism of a reaction may contain several steps. The step which occur very slowly, or the slowest step, right, it is called the rate determining step, right? So this reaction, rate of this reaction depends on this step. That's the meaning, right? And here, listen, if the forward reaction, see, it's a reversible, I put a reversible arrow here. Why? Because in this step, forward reaction, backward reaction will also occur. Forward step is ionization. In the backward direction, these ions may recombine and forms the substrate. Backward also will occur. But to get more product, these ions should be stable. If the ions are highly stable, if the ions are stable enough, then they undergo further reaction. They usually do not participate in the backward reaction. Okay, so in this reaction, carbocation stability is very, very important. If carbocation is more stable, then forward reaction occurs in larger extent compared to backward reaction, right? That is why in this Sn1 reaction we usually take polar protic solvent. Here we have taken water as solvent. You know very well, water is nothing but polar protic solvent. Polar protic solvent can stabilize both the cation and anion. Okay, so polar protic solvent stabilizes, right here, it stabilizes both cation and anion. So both these ions get stabilized. Since the ions get stabilized because of the solvent, this reaction occurs, okay, larger extent in the forward direction, or this ionization takes place only in forward direction, I can say. Okay, the backward, that is the recombination of ions, that is extremely, it occurs in extremely small extent. So we need not bother about that. Okay, that is why in Sn1 reaction normally we prefer polar protic solvent, because it can stabilize both the ions. Therefore backward reaction or the backward step, right, occurs in very small extent. That is what we want actually. We want more amount of carbocation. Okay, and in the rate determining step, okay, it involves substrate and carbocation, okay, your solvent. Therefore rate of this reaction, okay, is decided by your substrate, your the carbocation that is formed, and the solvent, and it also depends on the temperature. Okay, we will discuss that as we go along. And before going further, let me give one more information here. See, in the substrate molecule, the carbon that contains the leaving group, that is bromine atom, this carbon is connected with the 4 sigma bonds, right? Single bonds. You know very well, single bonds are usually sigma bonds, right? Therefore all these 4 bonds are single sigma bonds. So this carbon should have sp3 hybridization. You know very well, if a carbon has 4 single bond, hybridization of the carbon should be sp3. sp3 means the structure should be tetrahedral. So around this carbon, okay, tetrahedrally these groups are arranged. That's the meaning. Around this carbon, all these 4 groups are arranged in a tetrahedral manner. Tetrahedral. Okay. Whereas when the carbocation is formed, now this carbon carry only 3 sigma bonds. Okay, the carbon carry only 3 sigma bonds. Therefore hybridization of this carbon is sp2. right? sp2, you know, sp2 means it is trigonal planar, or simply planar, right? I'll write trigonal planar. So these three methyl group exist in a triangle position, and all the three methyl groups are in a single plane with the carbon atom. See what I'm trying to say? Carbon and all the three methyl groups are exist in the same plane. Okay, so tetrahedral molecule becomes a planar molecule. This is the first change occur, right, in the Sn1 reaction. In Sn1 reaction, tetrahedral molecule becomes, okay, in the first step it becomes a flat ion, carbocation. Okay, right. So this is the first step. First step is the slow step, and that is the rate determining step in Sn1 reaction. Okay, then is there any doubt up to this? Is there any doubt?
No, sir.
Okay, right. Now, what about the second step? Step 2. In step 2, the carbocation that is formed, we get a planar carbocation now. We have a planar carbocation. It is all these atoms, groups, all are existing in same plane. It's a planar. Now the nucleophile, that is hydroxide ion present in the solution, act as a nucleophile. Okay, I told you nucleophile should contain at least one lone pair. Students, keep this in mind. Nucleophile should contain at least one lone pair. Hydroxide ion, in which the oxygen atom has 3 lone pair. Using one of the lone pair, it can attack this carbocation carbon, that is carbon carrying positive charge, either in the top side, or it can attack from the bottom side. This dotted line, students, observe this carefully. This thick line indicate OH is approaching this carbon from the top side, and the dotted line indicate the OH ion, hydroxide ion, approaching from the bottom side. So here this carbon is attacked in two manner with the equal probability. There's a 50-50 probabilities there. So 50% of the hydroxide ion attack from the top side, 50% of the attack ion may attack from the bottom side. Therefore we get two types of product. Listen, in this case you cannot distinguish whether it is top side attack or bottom side attack, because I have taken tertiary butyl bromide. But if you take asymmetric carbon, suppose if the carbon carrying halogen, if it was an asymmetric carbon in the substrate, then this reaction will give you two different isomeric product. Okay, we'll discuss that as we go along. But now keep this in mind, this OH minus ion attacking this carbocation in two different manner. Keep that point in mind. So what's the product? The product is this. In this case, whether it is top side attack or bottom side attack, you will get the same product. You will get only single product, no isomer. And remember, this step occurs, okay, in an irreversible manner. Because this OH cannot ionize again. It cannot ionize because the electronegativity difference is not so high. Okay, so this reaction does not occur in the backward side. It occurs only in the forward side, and this is a fast step. This step is the fast step in this reaction. So I have told you Sn1 reaction occurs in two steps. Step 1 is slow. Step 1 occurring in slow manner, whereas in step 2 the reaction occurs in a fast manner. And remember, slowest step decides the rate. That's why the first step 1 is called rate determining step. Okay, yeah. So keep all these points in mind. Now, so this is Sn1 reaction. In Sn1 reaction, first step is a reversible step, and slow step, that is the rate determining step. Second step is a fast step. Okay, we usually do not focus on fast steps. We focus, right, most of the time we focus on the step 1, that is a slow step, right? Now what I'm going to do, what are the factors affecting the rate of Sn1 reaction? Factors influencing or affecting the rate of Sn1 reaction. Students, keep this in mind. Sn1 reaction occurs with the two-step mechanism of Sn1 reaction contains 2 steps. Okay, keep that point in mind. Now what are the factors? Number 1, as I told you before, in the rate determining step, what are the species involved? Substrate is there, carbocation is there, and the solvent, polar protic solvent is there. So all these definitely affect rate. So let me start with the substrate first. Nature of the substrate. Nature of the substrate. Students, observe this carefully. The substrate, if it ionizes, it should produce a stable carbocation. You know very well, this carbocation is a tertiary carbocation, correct? Because carbon carrying positive charge, it is directly connected to 3 carbon. It's a tertiary carbocation. And if you see the carbocation stability, listen, stability of carbocation, this is a general order stability of carbocation. If you compare, tertiary carbocation is more stable compared to secondary, very stable compared to secondary. Secondary carbocation is more stable than primary. Primary carbocation, okay, is more stable than methyl carbocation, methyl cation. This is a general order, keep this in mind. Tertiary carbocation is highly stable. Okay, so here what we want is this ionization should occur. For ionization to occur, the carbocation should be highly stable. Then only this ionization occurs readily. Therefore, the substrate which can produce very stable carbocation undergoes this reaction fast manner. Simple. Substrate which can produce very stable carbocation undergoes Sn1 reaction in a fast manner. Okay, so using this idea, if you compare different halides, okay, tertiary halides, let me write here simply 3 degree Rx, which means tertiary halides. Tertiary halides undergoes Sn1 reaction in a fast manner. Then secondary halides, then primary halides, finally methyl halides. Actually, primary halide and methyl halides, okay, usually they are not preferred for Sn1 reaction. Students, keep this in mind. Methyl halides, because methyl halide will give very less stable carbocation. Primary halide also will, compared to this, the carbocation stability is very poor. So primary halides and methyl halides, they are not good substrate for Sn1 reaction. For Sn1 reaction, the highly preferred substrate is tertiary halide or any other halide. Okay, we have allyl halide, we have benzyl halides. We are going to discuss that. Allylic halides, benzylic halides are also preferred because they also produce stable carbocation. But I have taken these halides, tertiary, secondary, primary. Among this, tertiary halides are very highly preferred because tertiary halides produce tertiary carbocation which is highly stable. Okay, so this is the first point you should keep in mind. Right, now I'll give other substrates where Sn1 reaction occurs readily. Okay, Sn1 reaction preferred substrate for Sn1 reaction. Okay, I have told you tertiary halides, right? You take any tertiary halide R, tertiary halide. Tertiary halides are preferred substrate, no doubt. Number 2, tertiary halide. We write this shortly like this, tertiary halide. Then allylic halides. Okay, what is allylic halide? Halogen attached to an sp3 carbon. If this sp3 carbon directly connected to a doubly bonded carbon, we call this allylic. Allylic halides are also preferred substrate for Sn1 reaction. Why? Because in allylic halide, if this halogen comes out as X minus, you will get a carbocation, allylic carbocation. Okay, you will get an allylic carbocation. This allylic carbocation is highly stable by resonance. Okay, due to resonance, this allylic carbocation is highly stable. Therefore, allyl halides or allylic halides are also a preferred substance for Sn1. Preferred substrate. Then benzylic. What is benzylic? Benzene connected to an sp3 carbon, and that sp3 carbon is connected to an halogen. We call this as benzylic. This is allylic halide, and this is called benzylic halides. Benzylic halide. Okay, tertiary halides, allylic halides, benzylic halides, these are all preferred substrate for Sn1 reaction. Here, this halogen, when it comes out as X minus, you will get a carbocation like this, plus charge. You will get a benzylic carbocation. This benzylic carbocation is stabilized by resonance again. This is stable. This cation is stable due to resonance. Okay, you can write many possible resonance structures for this, right? So because of resonance, this carbocation is highly stable. Therefore, benzylic halides are also preferred substrate for Sn1 reaction. Okay, so students, keep this in mind. These three are highly preferred for Sn1. Okay, then second point. Okay, so in the first point I said carbocation stability decides the reaction rate of the reaction. If carbocation is more stable, then rate will be high. Now students, if you observe carefully, listen, if this is your substrate, from the substrate the halogen or the leaving group, let me call it as a leaving group should come out readily. Okay, so nature of the leaving group also decides. If you have a better leaving group comes out quickly, you will get carbocation readily. Okay, so nature of the leaving group also decides. Let me write the next page. Yeah, nature of the leaving group. Let me put simply LG. LG means leaving group. Nature of the leaving group. Okay, listen, among halogens, suppose if you take alkyl halides, among halogen, you know very well, alkyl iodide is a better leaving group or best leaving group compared to alkyl bromide. Alkyl bromide is better compared to alkyl chloride. Okay, then alkyl fluorides are not preferred for students. Alkyl fluorides are not preferred for nucleophilic substitution reaction in general. Sn1 or Sn2 or whatever it is, we do not prefer as alkyl fluorides because fluorine or fluoride is a very poor leaving group. Keep that in mind. Okay, so alkyl halide in which iodide is a better leaving group. So if you take tertiary alkyl iodide, tertiary alkyl bromide, tertiary alkyl chloride, if you compare, tertiary alkyl iodide will undergo Sn1 reaction faster. Why? Because iodide is a good leaving group. Okay, so rate of Sn1 reaction is directly proportional to nature of the leaving group. Okay, nature of the leaving group, meaning better leaving group will come out faster. Okay, better leaving group, okay, increases the rate. If you have better leaving group, then rate of the Sn1 reaction increases. That's the point. Okay, keep this in mind, very, very important.
Sir?
Yes?
Sir, I didn't get my marks yet, sir.
Okay, ma, let me check. Let's just, right, ma?
Yes.
Yeah. Then, next point.
Sir, 1 second, can you show the previous page, sir?
Yes.
Thank you, sir.
Yes, ma'am. Now, third point, after nature of the leaving group, third important point is about the nature of the nucleophile. Nature of the nucleophile. Students, observe carefully. Is nucleophile involved in rate determining step? Check it. Is nucleophile, what is a nucleophile in this reaction? Hydroxide ion. Is hydroxide ion participating in step 1 or in the rate determining step? Just check and tell me.
No, sir.
No, right? That means rate of the reaction, it is independent of nucleophile. Rate of the reaction is independent of nucleophile. Okay. Rate of Sn1 reaction, right? Rate of Sn1 reaction, it is independent of nature of nucleophile. But students, keep this in mind. Strong nucleophile, if you say a nucleophile as a strong nucleophile, okay, most of the time strong nucleophile can also act as a strong base. Students, observe this carefully. Strong nucleophile may also act as strong base. If it is a strong nucleophile, it will show nucleophilic substitution reaction. If it is a strong base, it will also show, or a strong base shows elimination reactions. Elimination is a different type of reaction. So most of the time, strong nucleophile can also act as a strong base. Therefore, not only nucleophilic substitution reaction occurs, along with nucleophilic substitution reaction, elimination also occurs. If you want to avoid this, right? If you want to avoid elimination, because our focus is nucleophilic, we want only nucleophilic substitution reaction to occur. If you want to avoid elimination, then the preferred substrate for preferred nucleophile for Sn1 is the weak nucleophile. Why? If it is weak nucleophile, because see here, for Sn1 reaction, rate is independent of nucleophile. You can take weak nucleophile, strong nucleophile, anything you can take. But if you take strong nucleophile, most of the strong nucleophile act as strong base. Most of these strong nucleophiles can also act as strong base. So elimination will occur. To avoid elimination, okay, it is preferred to take weak nucleophile in Sn1 reaction. So for Sn1 reaction, weak nucleophiles are preferred. Weak nucleophiles are preferred. Okay, student, note down, very, very, very important. See, I am not saying that nucleophile is directly affecting the rate. No. Nucleophile, if you choose strong, you can take either weak nucleophile or not strong nucleophile. Nothing wrong in it. But there is another problem occurs here. If you choose a strong nucleophile, most of the time strong nucleophile can also act as a strong base. That strong base will give you some unwanted reaction, elimination reaction. So when you carry out a reaction along with the nucleophilic substitution reaction, elimination also occur. If you want to avoid that elimination, okay, you should choose weak nucleophiles. If you choose weak nucleophile, you can avoid that. Okay, and examples for weak nucleophile, let me write here. There are several examples available. I'll give one or two here. Examples: water. I have told you sometimes solvent itself acts as a nucleophile. Water, alcohol, these are all examples for weak nucleophiles. Note down. So for Sn1 reaction, yes.
So to avoid elimination reaction, we use weak nucleophiles. Right?
Yeah. Yes. 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 Okay, so for Sn1 reaction, weak nucleophiles are preferred. Examples for weak nucleophiles: water, alcohol, etc. Students, keep this in mind. This is very important. Rate of the reaction is independent of nature of nucleophile. That is the main point you should keep in mind. But why we are preferring weak nucleophile? The reason is, if we choose strong nucleophile, okay, some unwanted reaction also occur. To avoid that, we are choosing weak nucleophile. Okay. Then the next one, point number 4. This is about, so we have I have given information about nature of the substrate, nature of the leaving group, then nature of the nucleophile. Okay, then fourth one, nature of the solvent. Which solvent we should prefer for Sn1? Students, you should I have told you already this point. In the rate determining step, we are generating two ions, a cation and an anion, right? For we want the forward step to occur in larger extent. We don't want the backward step, because in the backward direction, carbocation combine with the Br minus, so that you will get a substrate. So carbocation concentration will decrease. Okay, therefore, to increase carbocation concentration, okay, we should stabilize. Somehow we should stabilize the carbocation and we should stabilize the the anion. Okay, if you want to stabilize both these ions, then the preferred solvent is polar protic solvent. Okay, so let me write here polar protic solvent. I'll write simply PPS. Polar protic solvent favors Sn1 reaction. Why? Because it can stabilize both the carbocation and the anion. Okay, so it helps in ionization and also stabilize the ions. Polar protic solvents, okay, helps ionization, and also stabilize the ions. I'll write simply ions, means cation as well as anion. It will stabilize both ions. Therefore, polar protic solvents are preferred in Sn1 reaction. Examples for polar protic solvent: examples, water is a polar protic solvent, alcohol is a polar protic solvent, right? We have many examples actually, right? Take down. And students, I told you already, sometime the solvent itself can act as a nucleophile. Okay, in most cases solvent act as a weak nucleophile, right? Whenever solvent act as a nucleophile, we call those reactions as solvolysis reaction. Okay, solvolysis. This is also one important point you should keep in mind, right? So so we have discussed the main points. Then one more point which I forgot to tell you. This is not supposed to be discussed under point, but this is a very important one. Rate of this reaction. Students, observe carefully. In the step 1, See, in the rate determining step, in the reactant side, we have only the tertiary halide. We have only the substrate. We don't have the nucleophile here, correct? In step 1 or in the rate determining step. So, rate of this reaction is directly proportional to concentration of the substrate. S-U-B-S-T-R-A-T. Concentration of the substrate, and it was found experimentally that the power, okay, concentration power is actually 1. It was found experimentally, right? So Sn1 reaction, students observe carefully, Sn1 reaction, it is not only first order. Since the power is 1, it is first order. It is first order reaction. Sn1 reactions are first order reactions. It is not only first order, okay, in the rate determining step. See, in the rate determining step, only one molecule of substrate is participating. No nucleophile, okay, no other species, right? Only substrate molecule is participating. Therefore, the reaction is also unimolecular.
So what is first order reaction?
Yeah, we'll discuss in chemical kinetics, ma. In chemical kinetics chapter, we'll discuss that. But right now, listen, experimentally you can determine, okay, this is called called rate law. Okay, in rate law, rate of any reaction is directly proportional to concentration of the reactants. Okay, we'll see how to write the rate law and all as we go along in chemical kinetics chapter. We are going to discuss that. But right now, keep this in mind. The power term, okay, here we have substrate concentration. The power term should be determined through experiment. Experimentally, it was found that in Sn1 reaction, the substrate concentration power value, power of substrate concentration is 1. Okay, that is nothing but order of the reaction. So Sn1 reaction follows first order kinetics. Not only that, in the rate determining step, in the reactant side, only one molecule is participating, so it is unimolecular reaction. So Sn1 reaction is not only first order, it is also unimolecular. Okay, student, actually I am not supposed to discuss this under factors affecting rate. I forgot to say in the front, that's why I'm giving you here. Okay, I'm giving the information, right? Yeah. Now, next important point is that potential energy diagram. Let me draw in the next page. Potential energy diagram. Usually they won't discuss in books, but this is very, very important. Potential energy diagram for Sn1 reaction. How the potential energy diagram look like? See, if I plot potential energy, okay, of the species involved in the reaction versus reaction coordinate. Reaction, okay, this is reaction coordinate. Reaction coordinate. If I plot potential energy versus reaction coordinate, students observe this carefully. In the Sn1 reaction, initially we have the substrate, okay, that is alkyl halide. Initially we have alkyl halide, and we also have nucleophile, okay, but the substrate and the nucleophile, they have some average potential energy here. When the reaction starts, what will happen? When the reaction starts, when ionization starts, okay, the potential energy increases, reaches a maximum, and then decreases and forms an intermediate. Then that intermediate again undergoes further reaction, so that potential energy increases and forms the product, final product. Final product is alcohol, ROH. Okay, alkyl halide become alcohol. This is the potential energy diagram. Listen, students, observe this carefully. In a potential energy diagram, if you get a shoulder type peak or curve, that corresponds to the formation of an intermediate. It corresponds to the formation of intermediate. What's the intermediate? Here, carbocation is the intermediate. carbocation that is formed is the intermediate. So keep this in mind. In the rate determining step, that is in the first step, you will get a carbocation. This carbocation is called an intermediate. What is an intermediate? Intermediate is a species which can be detected through experiment. You can isolate also. Okay, what is mean intermediate? Intermediate can be detectable. Using through experiment you can detect. You can also isolate. That's the meaning for intermediate. Intermediate means intermediate is a species that is formed during the reaction. You can using experiment or using some instrumental methods, you can detect the intermediate. You can also isolate the intermediate. So here in Sn1 reaction you are getting an intermediate. Whenever intermediate is formed, students, you will get a shoulder type. You will get a shoulder type curve like this. Shoulder. Okay. And see this carefully. This peak is called transition state 1. This peak corresponds to transition state 2. Students, observe this carefully. Normally people say that only in Sn2 transition state will come. Sn1 they never speak about transition state, but keep this in mind. In Sn1 we have two transition states actually. Between substrate, this is substrate, okay, this is substrate, and this is your product. Okay, between substrate and the intermediate we have one transition state. Between intermediate and the product we have another transition state. So there are two transition states involved in Sn1 reaction. So keep this in mind. In Sn1 reaction, okay, we have one intermediate. Students, observe this carefully. It is not necessary that only one intermediate should form in a reaction. In some reaction you may get two intermediate, you may get three intermediate, it depends. But in Sn1 reaction we get one intermediate and we get two transition states. What is meant by transition state? Transition state is hypothetical. You cannot detect this. Transition state cannot be detected. You cannot detect this. You cannot isolate. Cannot be isolated. You cannot detect. You cannot isolate. Okay. Through some computational method, you can say that a transition state like this transition state appear, or the transition state look like this. You can say, but you cannot prove it through any experimental technique. Okay, that's the difference between transition state and intermediate. See, intermediate is detectable. You can isolate. Whereas transition state you cannot detect, you cannot isolate. That's the main point you should keep in mind. Okay, students, is this clear? Any doubt? Any doubt?
No, sir.
Yeah, good. Now here another important point I like to say. It's a very important point. See, you are getting carbocation, right? Whenever carbocation is formed, okay, in Sn1 reaction we get carbocation. Students, you should keep this in mind. Whenever carbocation is formed, there is possibility of rearrangement. Okay, there is a possibility of rearrangement. So rearrangement may occur. Depending upon your carbocation. Okay, depending upon the carbocation, sometime rearrangement may occur. Right? We'll discuss that as we go along. Okay, with some examples. Right? So this is the point you should keep in mind. Okay, then is this clear, student? Up to this, any doubt? If you have any doubt, please tell me. I will help you. If not, we'll move further. Right, ma. Good. Now, okay. Now we'll discuss Sn2 reaction. We'll discuss Sn2. Then we'll take some examples for Sn1 and we'll take some example for Sn2. We'll analyze. Okay, why some reaction occurs in through Sn1, why some reaction occurs through Sn2 and all. Okay. Yeah, I forgot to say one more point here. This is another important point, point number 7. Students, observe this carefully. This is another important point. Suppose if I choose some tertiary halide, I'll choose some tertiary halide, R1, this is R2, this is R3. Yeah, students, turn on your camera. Students, turn on your camera, all of you. Yes. Hello, students, turn on your camera. Okay. Now see, I have taken some tertiary halide now. Here we have halogen atom, it's a leaving group, and here we have some group R1, some group R2, some group R3. Assume that R1, R2, R3, they are all not same group. R1, R2, R3 are different. If all the 4 groups are different, we call this carbon as, what is the name of that carbon? If a carbon attached with, yes?
Chiral carbon.
Yeah, very good. Chiral carbon or asymmetric carbon. Very good. It is a chiral carbon. Chiral carbon. Okay. Chiral carbon. Okay, the reactant has a chiral carbon, so it will have some configuration. This chiral, whenever a molecule has a chiral carbon, that chiral carbon has some specific configuration. It may have R configuration or it may have S configuration. Okay, R and S are called configuration. Right, depending upon if a molecule has a chiral carbon, okay, there is a specific arrangement of these groups around the chiral carbon, which gives you a particular configuration. Okay, the configuration may be R or the configuration may be S. Suppose if I take the reactant with R configuration alone, right, if I carry out the reaction with the R configuration alone, I am not taking S, only R. Okay, I am taking the molecule having R configuration alone. If you carry out the reaction, Sn1 reaction, okay, I told you first step is X will come out, you will get a carbocation, then you will get planar carbocation, then nucleophile will attack from the top side as well as from the bottom side. So you will get 2 types of product. Let me show the product like this. OH may attack from the top side, R1, R2, R3, or the OH may attack from the bottom side. Just for understanding purpose I am showing like this. You will get 2 different products. Suppose if this product has R configuration, suppose, then the other product has S configuration. Your reactant has only R configuration, but the product we get has R as well as S. And I told you there is a 50% chance for top side attack and 50% chance for back side attack. Therefore, R and S are formed with equal amounts, 50-50. Students, observe this carefully. In the product, we have alcohol, right? Both are alcohol and they are isomers. R and S are isomers of the same product. Therefore, if I get 50% of this and 50% of this, what type of mixture I'll get? Suppose if the molecule having R configuration, suppose Suppose if molecule having R configuration rotates the plane polarized state in clockwise, the molecule having S configuration will rotate the plane polarized state in anti-clockwise. Suppose. Students, I repeat, R configuration need not rotate clockwise, plane polarized state in clockwise alone. It can also rotate in anti-clockwise. Just for understanding purpose, I'm saying like this. Suppose if this R configuration of the product rotate the plane polarized state in clockwise, then the S configuration of the same product, okay, will rotate the plane polarized state in anti-clockwise. So what about the net rotation? And I have 50-50.
0, sir.
Yes, net rotation is 0. So this mixture is optically inactive. This mixture is optically inactive. Okay, listen. What is the name of this mixture? If it has 50% of one isomer and 50% of other isomer, which can rotate light in equal extent in the opposite direction. What's the name of that mixture? If a mixture contains 50% of R isomer and 50% of S isomer of the same compound, that mixture is called as dash.
Racemic mixture.
Yeah, very good. That mixture is called racemic mixture. That mixture is called racemic mixture, and this reaction leads to racemic mixture, correct? So this reaction, Sn1 reaction, is often called or often leads to racemization. Note down. Sn1 reaction leads to racemization. Sn1 reaction leads to racemization. Is this clear, student? Any doubt? Any doubt, students?
No, sir.
Right, good. Yeah, so this is another important point you should keep in mind. Sn1 reaction leads to racemization. But in some Sn1 reaction, okay, I am not going to discuss that here. In some Sn1 reaction, one product will be little more than the other. One isomer is little higher than other isomer in the final mixture of in the final product. Okay, in some Sn1 reaction, one isomer, okay, may be a little higher than the other isomer in the final product. Okay, this is due to the formation of tight ion pair, which I am not going to discuss here. It is due to tight ion pair. Due to tight ion pair, sometime one isomer may exist in little larger extent, little larger amount compared to the other. Okay, what is meant by tight ion pair? Simple. See, here you will get ions, right? The first step, you will get carbocation and anion. Sometimes these ions have opposite charge, correct? So they are attracted. So the bromide ion, sometimes the ion may not comes out quickly due to electrostatic attraction. This ion tightly attracted with this ion. The anion tightly attracted by the cation. Okay, so due to this tight ion pair, right, the OH minus nucleophile prefers to attack, okay, in one side compared to the other side. Okay, it should attack the OH minus. See, in the second step, OH minus should attack. If the tight ion, if the anion is not leaving, suppose if the anion is present in the behind the plane, okay, it is tightly attaching with the carbocation, then most of the OH minus prefers to attack from the top side. Therefore, one isomer will be formed in little excess amount compared to other. But this is a special case. We are not going to discuss that here. Okay. Anyway, keep it in mind. Keep it in mind. Okay. In general, Sn1 reaction leads to racemization, but in some cases, okay, in some rare cases, right, you may not get, you may get inversion, right, in little amount. Okay, you will get inversion product. We'll discuss that later. Okay. Yes. This is a very essential point. Keep this in mind. If in the question paper, if they ask, you should read the options carefully. Sn1 reaction in general leads to racemization, no doubt. But in some cases, along with the racemization, some inversion may also occur. Inversion. Okay. Along with the racemization, some small amount of inversion also occur. Right. That point you should mention. Right. Usually in JEE Advanced they ask this question. Right. Okay. Yeah. Keep this in mind. Now let me go on to the next one, that is Sn2 reaction. Sn2 reaction. What is Sn2? 2 means bimolecular, N means nucleophilic, bimolecular, nucleophilic, S represents substitution reaction. Okay, bimolecular nucleophilic substitution reaction. Okay, I'll take an example for this. The best example for Sn2 is methyl halide. You take methyl halide or any primary halide. Let me take methyl bromide. To this, add aqueous sodium hydroxide. Now, what will happen? And here also the bromine will come out, OH minus will attack. Right? So bromine is replaced by OH, or bromine is substituted by OH. You will get CH3OH methanol, along with you will get Br minus plus Na plus. These are the product. This is the reaction. This is an example for Sn2 reaction. Now, if you see the mechanism, of Sn2 reaction, students observe carefully. Mechanism of Sn2 reaction contains, or the Sn2 reaction occurs in a single step. Sn2 reaction occurs in single step, only one step. Sn2 reaction occurs in single step. Sn1 occurs in two step, whereas Sn2 occurs in single step. Okay, what is the mechanism? Let me show that. Since it is single step, so first I'll take the methyl halide. I'll show you methyl halide like this. It has 3 hydrogen atoms and a leaving group bromine. Now this sodium hydroxide will ionize to give Na plus OH minus. You know very well OH minus is the nucleophile here. So OH minus, let me write OH like this, OH. This oxygen atom has 3 lone pair with a negative charge, OH minus. Now what will happen? This OH minus donate one of the lone pair, or using one of the lone pair, it attacks the carbon carrying the halogen. Okay, so you will get a new bond. A new bond starts to form between this oxygen and carbon, and this bond starts to break. That is, the bond between carbon and bromine starts to break. These two occurs simultaneously, which we cannot detect through instrument. You can say only through computational method. Computationally, yes, this between carbon and oxygen a new bond starts to form, and between carbon and bromine this bond starts to break. So breaking of CBr bond and formation of COH bond occurs simultaneously. This you can show only through computational method, not through any experiment. Okay, so you will get this bond starts to break. So I'll put it in dotted line, starts to break, and you'll get a new bond between OH group and the carbon. See, initially this oxygen carry full negative charge, but when it starts to donate the lone pair, the negative charge on oxygen will diminish. So the negative charge now become partial negative. Initially here the bromine atom is neutral. When it starts to pull the bond pair, okay, electron density on bromine starts to increase, so you'll get partial negative charge on bromine. Don't put one side negative and the other side positive, students. Keep this in mind. Both are negative charges, partial negative, partial negative. Okay, and listen, student, this is not, you cannot detect through any experimental method. You cannot isolate. This is an hypothetical structure that we give. Through computational method, people have found this. So this is called a transition state. This is called a transition state. Students, I repeat, transition state is not considered as a species. It is not a species that is formed. It is an hypothetical structure. It is hypothetical. Then what will happen? This Br comes out, you will get Br minus, and OH forms bond in the back side. So you will get a product like the CH, 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 OH. You will get a product like this. Don't think that I have two arrow mark here, therefore it is a two-step reaction. No, this is not considered as a species. This is a hypothetical structure, therefore it is a single step. Okay, so people normally think here we have one arrow mark, here we have one arrow mark, so they may say that it is a two-step. No, because the transition state is not a species. So you should consider only this arrow mark. You need not worry about this. So this is the arrow mark. So we have single step, and this is the slow step in the reaction. This occurs in slow manner, and this is the rate determining step, RDS. RDS, rate determining step. Take down. Okay, and the notable point here is, students, observe this carefully. Nucleophile attacking the substrate. This is your substrate. This is substrate. In substrate, bromine is the leaving group. I'll put Lg here. Lg means leaving group. Nucleophile attacking the substrate or substrate carbon from the back side of CBr bond. See this? Note this carefully. CBr bond is here, but nucleophile is attacking from the back side. So Sn2 means backside attack. Keep this in mind. Sn2 means backside attack. Nucleophile attacking from the backside of CBr bond, or the bond connecting the leaving group. Right? So this is the mechanism. Now we'll discuss some points here. Students, any doubt in this? Any doubt? Any doubt? Yeah?
No, sir.
Right. Next. Here, rate of this reaction. Students, observe carefully. In the rate determining step, see, in the reactant side, we have the nucleophile, we also have the substrate. Two species are involved. So it is bimolecular. Not only that, experimentally it was found that the rate law for this reaction is, rate is directly proportional to concentration of the substrate and concentration of the nucleophile. Nucleophile here, in this case, nucleophile is OH minus, but in general we'll write nucleophile. And it was found experimentally that this power is 1, this power also 1. Student, these power values are determined through experiment. Okay, so in an for an Sn2 reaction, rate depends on the concentration of substrate as well as the concentration of nucleophile. Okay, now Listen, so in Sn2 reaction, what is the order? Here order is 1, here order is 1, so 1 plus 1, 2. So Sn2 reaction is a second order reaction. Sn2 reaction is a second order reaction. And in Sn2, in the rate determining step, two species are involved. The substrate molecule and the nucleophile. Only two species are involved, so it is a bimolecular reaction. Sn2 reaction is a bimolecular reaction. Right? This is another essential point, keep this in mind. Sn2 reaction is a bimolecular reaction. Okay, then. Now, we'll discuss what are the factors affecting the Sn2 reaction. Okay, and before going to that, students, here see in the transition state, these four atoms, that is this hydrogen, this hydrogen, this hydrogen and the carbon, these four atoms are present in one plane, and this dotted bond and this dotted lines, they are perpendicular to that plane. I repeat, carbon and the three hydrogen, okay, these four atoms are present in one plane, and these dotted lines, okay, are perpendicular to that plane, and these are exactly opposite to each other. They are exactly opposite. They are not only perpendicular, they are exactly opposite to each other. Okay, that is the structure you should keep in mind. Okay, that's the structure of the transition state here. Okay, so in Sn2 reaction involves only transition state, no substrate. Sn2 reaction, okay, Sn2 reaction has only a transition state. Only a transition state, no intermediate. No intermediate in Sn2 reaction. We have only transition state. And remember, transition state is an hypothetical structure. It's an hypothetical structure. Right? Now, what are the factors? I'll just finish off the factors. Factors affecting rate of Sn2 reaction. Students, take down. Factors affecting rate of Sn2 reaction. Number 1, nature of substrate. Nature of substrate. Students, observe this carefully. Nucleophile, see here OH minus is the nucleophile. Nucleophile should attack this carbon comfortably. See why I chose methyl bromide, because in methyl bromide, see this carbon has only 3 hydrogen, and you know very well hydrogen atoms are negligible size. Hydrogen atoms have negligible size, so you need not worry about the size of hydrogen atom. They are negligible. You can imagine that there is no hydrogen at all. Therefore, the OH minus can comfortably approach this carbon, and it can attack the carbon and form, and the reaction will occur. Suppose instead of hydrogen, if I have any other group, what will happen? Steric hindrance will come. Nucleophile cannot approach, or nucleophile is not easily approach that carbon. It becomes difficult. Therefore, in Sn2 reaction, we always preferred methyl halide as substrate. Okay, I'll write here. So, if you compare the rate for Sn2 reaction, rate of Sn2 reaction, if you compare, listen, methyl halides are very suitable substrate. Very suitable substrate, because this carbon has only 3 hydrogen, and nucleophile can easily approach. Okay, it is a very suitable substrate. Then primary halides. Okay, then secondary halides. Secondary halides. Students, observe this carefully. Tertiary halides are very poor substrate. Normally, we say that Sn2 does not occur in tertiary halide. Okay, tertiary halides are very poor substrate. The suitable substrate for Sn2 is methyl halide and primary halide. They are very suitable. Methyl halides and primary halides are highly preferred for Sn2 reaction because nucleophile can easily approach. Right? Then next important point, number 2, nature of leaving group. Nature of leaving group. See, leaving group is very important here because see, in the Sn2 reaction, when nucleophile attacks this carbon, the leaving group should come out. Suppose if it is a poor leaving group, what will happen? Students, can you answer this question? Suppose if the leaving group is a poor leaving group, right? Leaving group should depart, right? Should depart easily. If leaving group is a poor leaving group, it won't come out. Then what will happen? If the leaving group is a poor leaving group, students, turn on your camera. Suppose if the leaving group, students, suppose if the leaving group is a poor leaving group, then rate will decrease. Rate of the reaction decreases. So in Sn2 reaction also, like Sn1, in Sn2 reaction also, okay, you require a better leaving group, right? Better leaving group, okay, increases the rate of the Sn2 reaction, increases the rate of Sn2 reaction. Okay, so among halides, if you compare alkyl halides, alkyl iodide, alkyl iodides, in which iodide is a best leaving group among alkyl halides. So alkyl iodide, in which rate, if you compare the rate, alkyl iodide undergoes Sn2 reaction faster than compared to alkyl bromide, then compared to alkyl chloride, then compared to alkyl fluoride. Actually speaking, I told you fluoride is not a preferred substrate because fluorine is a very poor leaving group. Normally we won't prefer fluorine. Okay, so keep this in mind. Why alkyl iodide undergo Sn2 reaction faster? The reason is iodide is a better leaving group compared to bromine. Bromine is better leaving group compared to chlorine. Okay, so keep this in mind, very, very important. This is regarding nature of the leaving group. Right, then point number 3. So we have discussed about the substrate, leaving group, then nucleophile, nature of nucleophile. Nature of nucleophile. Nature of nucleophile. Students, this is another important point. In the rate determining step, nucleophile is participating. The nucleophile should donate the lone pair and should attack the carbon. It should readily donate the lone pair. That means it should be a very strong nucleophile. Strong nucleophiles are preferred in Sn2 reaction. I write here, rate of Sn2 reaction is directly proportional to strength of the nucleophile. Strength of nucleophile. Students, I am going to give you an essential point here. Just note down carefully. Rate of Sn2 reaction depends on the strength. Strength means whether it is a strong or weak. Strong nucleophiles are preferred. Right? Strong nucleophiles. Students, strong nucleophiles are preferred, but I have told you already, whenever nucleophile is strong, then same nucleophile can also act as a strong base. See this point carefully. Strong nucleophile can also be a strong base. Some strong nucleophile can also exist as weak base. Which one you prefer then? Try to answer this question, student. Strong nucleophiles are preferred for Sn2, no doubt in that. But in strong nucleophile, some strong nucleophile are strong bases. Some strong nucleophile also exist as weak bases. Then which one you prefer? If you prefer strong base, something will happen. I have told you already. Can you try to answer that?
Elimination reaction.
Yes, elimination will occur. Yes, you are right. So if you want to avoid, you should choose strong nucleophile. At the same time, you should be little careful that the nucleophile should be weak base, should also be a weak base. So in that sense, listen, I'll give you some nucleophile which are strong but weakly basic. Examples: strong nucleophile but weak bases. I'll give I minus iodide, cyanide Cn minus, then SH minus, then RCOO minus, etc., etc. See, these are all highly preferred in Sn2. Students, observe this carefully. These nucleophiles are highly preferred. Why? Because they are strong nucleophiles but weak bases. That is very important. There are some nucleophiles available which are strong nucleophile as well as strong bases. Say for example RO minus, NH2 minus, R minus, etc., etc. They are all strong nucleophiles as well as strong bases. We won't prefer this. Why? If you use these nucleophile, okay, then elimination also occur along with that. So we prefer, for Sn2, we prefer these nucleophiles because these nucleophiles are not only strong nucleophile, they are also weak bases. Okay, if the basic strength is weak, elimination reaction you can avoid to some extent. I'm not saying that you can avoid 100%. Okay, you cannot avoid 100%. Okay, to some extent you can avoid. Yes, that is very, very important. Right, this is regarding nature of the nucleophile. Okay, students, I stop here. We'll continue this in the next class with a little more informations. Okay, right. Any doubts, students, here? Do you have any doubt?